10 years, and first time in the US, and we decided to come to Austin. We thought it was a good place to come, a growing place to come. And we got a lot of help actually from Dave at Brecker, setting up the venue and getting this all sorted. So thank you to Brecker for that. And thank you to all our sponsors, of course, Cadence and Impress, who are our two main sponsors today, and they'll be presenting. Brecker and Doulos as well, and SemiWiki helped us advertise the event as well. And TestSolve is the organizer of the event. So you're very welcome. We do have to stick on time, and the reason we have to stick on time is because we've got a lot of people online and they expect us to come in at a certain time and finish at a certain time. So the total registrations are 947. We're hoping to get 172 people here today. There's a few more people to come, hopefully. About 666, but an ominous number, isn't it? 666 online, and of which there are a lot of students are there as well. So we do try and encourage students to join our industry. And 366 companies across 42 countries. So we were very pleased with that for our first time in Austin. Okay, and you're of course very welcome. So you should have an agenda in front of you. You've got a booklet. We've now started. Our first speaker is Vivek Vadula from ARM. And I know it's a big day for ARM, so we're very pleased to have Vivek here, and able to present, and ARM allowed him to present as well. And then we've got Alex Fujovic from Ericsson, and finally our keynote, one of our keynote speakers, Cadence, one of our platinum sponsors. So that takes you through to this morning, and then just, I won't go through the detail here, but if you're in the main track, you're staying here. If you want to go to training session, that's C, which is there. If you want to listen to UVA AMS, that's there. That takes you up to lunch. All back in here straight after lunch with Impress, Larry, Adnan, one of our sponsors, Brecker. We've got Balram from Broadcom, Hemendra from Bitstar. We have a break, and then we split again, main track in here, and back to training there, or VHDL verification there. Okay? I think everybody's got a booklet if they want. If you don't want a booklet, if you want to do it online, then you can go there, and you can. We can show that later as well. I'll leave that on the screen for a little while. But we're going to go straight into our first speaker now. Okay, and we will end this slideshow, and I'll make an introduction. Okay. So our first speaker this morning, our keynote speaker, is Vivek Vadula, who's a technical director at ARM. He leads the SDL methodology, architecture, and development for hardware IPs at ARM. Prior to this, he had several roles at Intel, NXP, and Oracle Labs, spanning the areas of formal verification, post-silicon validation, and hardware software co-verification. He holds a PhD degree in electrical and computer science from the University of Texas at Austin. And he's going to talk to us about safety and security challenges in hardware IP development. Okay.
Can you all hear me? Okay. Thank you very much, Mike. Thank you for inviting me to the first ever Verification Futures Conference here in the US, and also allowing me to share my thoughts on some of the challenges in software, in security and safety. So this is a picture from SemiWiki. I promise you this is the only marketing slide I have. And there's a reason for putting up this slide, as you will see. SemiWiki, I know, is also one of the media sponsors, but the ARM ecosystem, I guess a lot of you would have seen this picture. ARM is one of the foundational IP providers, along with several others that you see here. So what it means is the IPs that are developed by ARM and other providers, they feed into basically all the devices that go into data centers, mobile devices, automotive, Internet of Things, right? And at the last count, we have about 250 plus billion chips into which ARM has made it into. Now, there are also other IP providers that have been providing these, which means that all these IPs are integrated onto a chip, and they all need to work together. Now, in addition to providing just the performance and the feature set, it is also incumbent upon companies like ARM to be able to provide something with regards to safety and security, and provide a dependable system, a dependable set of IPs that can be integrated, right? So what does that take us? So some of the key pillars of dependable computing are functional correctness, and then the safety and security. But the functional correctness is something that a lot of us are familiar with. Here we are asking a question: does the system behave correctly under normal operating conditions? A different question, a different way of asking this question is, for every possible input, does the output satisfy the specification? Now we have pre-silicon methods such as simulation, emulation, and formal verification. And post-silicon, we have DFT, at-speed testing, board-level testing. A lot of us are familiar with this. I did my time too. Then we have safety and security as emerging pillars. Now these are not something new, but they've become more relevant as we have more IPs interconnected and working together on a lot of systems. So here we are asking the question: does the functionally correct system that we have verified earlier, does it behave predictably under adverse operating conditions? So if you have adverse conditions, if these adverse conditions are a result of Murphy's law, then we call that safety, right? In other words, I don't know, hopefully all of you are familiar with Murphy's law. Anything that can go wrong will go wrong, and at the worst possible time. Now, if these adverse conditions are due to the devil's law, which is what we refer to as security, and this is my definition: anything that can go wrong shall be made to go wrong at every possible time. Right? Okay, so jumping on to safety. So a colleague of mine has presented a lot of details about safety, requirements and conformance and the overall framework at the European conference. So I won't go into the details as to the ASIL levels, the ADAS, and things like that. I want to dive into the design and implementation aspects and what are the challenges here. Right. So let's take a simple example of an electrical power steering. Right. Here, you must continue, what we are trying to ask here is, we must continue to function or at least behave predictably in the event of a fault. What does predictable behavior mean? It means we need to be able to go into a safe state gracefully. You don't want it to stall in the middle of the highway. You want to make sure that we gracefully go into a safe state, bring the vehicle into a safe state, allow you to steer your vehicle, maybe get off the ramp and go to a safe place, right? And a functionally safe system aims at preventing hazardous behavior in the event of a fault. So if there's a fault, in addition to just detecting it, you want to make sure that that fault doesn't become a hazard. That's what you're trying to make sure. So what are some of the sources of these failures? So you can classify them into two broad categories. One is systematic failures. A lot of us are familiar with this, with these kind of failures, these are due to design faults, design errors, specification errors, software errors. And what you want to do is to make sure that there is a good amount of safety analysis to go about identifying what are the causes, and this is something that is traditionally covered in the functional safety management and culture. Right? But then there are these other kind of faults, which are random faults, or what some of us call as acts of God. The first kind is permanent faults, which are a result of silicon degradation over a period of time. And we detect these as part of our DFT, where you have some failures on the chip when the chip comes out, but this is in the field, right? And these are the kind of errors that can happen in the field that can actually affect the behavior of the system, affect the safety of the system, which in turn causes a hazard. And then there are these transient faults. They come and go away. Sometimes you don't know the cause. Sometimes you do know what the cause is, where it's a cosmic particle doing a bit flip, just lasts for a few minutes, enough, or a few seconds, enough for it to cause a hazard. So there is this concept of failure, fault tolerant time interval. What this means is when you have this normal operation going on, a fault occurs, right? And then you have a certain amount of time for you to detect the fault. So this is not just fault detection that you can take forever to detect. You have a certain amount of time during which you can detect the fault. And then you have a fault reaction time. You need to act on that fault, make sure that that fault doesn't become a hazard. And all this, within a certain amount of time, you need to bring it to a safe state. Because if you don't do either of these two, then and you take too long, it can become a hazard. And that's what you're trying to prevent. So this concept of fault tolerant time interval is a pretty important concept. Now, fault tolerant FTTI is for the whole product, not just for the IP. So at the IP level, you are dealing this in this zone, right? And then you want to make sure that all of this, the detection, happens well before you give the product enough time for it to react. You need to be able to detect at the IP level. You need to make sure that the product is aware of that, and it gives you and gives it enough time to get you into the safe state right here. All right. So this is a typical safety product development lifecycle. I've removed all references to any standards. This is a very generic safety lifecycle. Here, you're starting off with performing a hazard and risk analysis, or also known as HARA, right? And what you're doing here is you're trying to identify and classify the hazardous events that are caused by the malfunctioning behavior. And through doing this, you identify what are the safety goals for each of these hazards. These goals are high-level goals that you need to meet so that you don't so the product doesn't end up creating a hazard. Then you take these safety goals and identify what are the functional safety requirements. These are the functional safety requirements. You're still at a high level at the functionality, trying to define what should be the requirements so that this hazard doesn't exist. And then you take each of these functional safety goals and translate them into technical safety goals or technical safety requirements. These could be either hardware or software, right? And these are the requirements that come to us eventually, where as IP providers, design engineers, verification engineers, this is what we are dealing with. Excuse me. So in terms of mitigations, so for systematic failures, they rely on guidance on the methods for the design and testing, which a lot of us are familiar. There is a good amount of knowledge, and also management and culture. Again, this is something that my colleague has discussed in the European version of this conference. I don't want to get into too many details of this, but it's managed through sound design processes, verification, and finally assessment, whether we have met the goals or not. But then you have these random failures, right? They rely on having quantitative targets on the probability of the failure of a safety function and the number of faults that you detected. So a certain number of faults that you can detect and can react and can prevent them from becoming a hazard is what is what translates into how much of the safety level that you can provide in a particular design, right? And these are managed by by features in the design for fault detection and control. So what makes it challenging at the IP level, right? As if there are not enough challenges at the product level. So you have little or no context of how the IP is going to be used. A lot of times, these IPs are designed a lot earlier than the product where it's intended to be used. Right? We design IPs all the time. We get requests for IPs that were designed 10 years ago to be used in a safety product that will last for 10 more years or 15 more years. So that's where we are. So we have unknown operating conditions. We don't know what conditions this IP is going to go into, or the product that this IP is going to go into that is getting operated. It could be something in a satellite that will last for what, 20, 30 years, or it could be going into a mobile phone, or it could be going into something like an automotive design, right? So you could have false identification of the type of failures that you are thinking about. What kind of random failures can you think of when it's in a space shuttle? What kind of failures that you can think of in terms of the systematic failures 10, 15 years down the line, or if it's a new process, let's say it goes into a new process, right? And I can't plan out for the process that's going to come out 10 years from now. So the systematic failures, the kind of failures that you can have are very different from what you are aware of today. So what that does is it makes the hazard and risk analysis highly subjective and unreliable. You can make some assumptions. You can say, okay, these are the ones that I know I need to meet. These are the safety requirements. But the resultant safety goals and requirements become questionable at some point, right? Now the IPs are expected to be highly configurable because you want to be able to provide these IPs to multiple applications. So these are highly configurable. And so you might end up over-engineering this. So a simple example is a dual lockstep. This is a common way where you replicate the design and then you XOR the outputs and check if that XOR value is ever going to be 1, which means there is something wrong with one of them, right? And use that as a detection mechanism. But that's like an over-engineering. That's an overkill for many applications. And then you have long duration of the products in the field. I already talked about this. 15 plus years in automotive. Satellite applications, it's even more, right? 25 years. So what are the chances of random failures 20 years from now, 25 years from now? Pretty high, right? I mean, as you look down the life of the project, of the product. So first challenge, getting the assumptions of use right? This is a challenge. I'm not saying I have a solution. My goal here is to present the challenges and share with you the challenges of what you are dealing with at the IP level. First of all, identifying what are all the potential use cases where this IP is going to be used. Is it even possible for us to imagine all the potential use cases for a particular IP? Operating conditions where the system is going to be deployed. Yes, you can imagine many operating conditions that we know of today, but those conditions might change. There might be extreme stress, thermal stress, other kind of stresses, right? The end of life for each of these use case. So we design the IP, let's say, okay, it's going to be licensed for the next 10 years, or it's going to be, the products are going to start using. But maybe 15 years down the line, there might be a new use case for which this IP is relevant. So what should be the assumption that I need to make about that? How it's going to be used? What are the implications at the IP level? Then the safety functions that I want to enable. What safety functions need to be enabled? Because this is coming from the hazard and risk analysis. And then finally, what is the probability of failure of the safety functions? So getting all of these right is one of the biggest, or the set of challenges is what I put together as assumptions of use. What are the assumptions that we can make about the IP so that we get the safety functions and implementing it correctly and implementing the appropriate safety mechanisms in the IP. Then you have the safety, implementing the safety requirements themselves. right? Safety is often impacted by the interacting entities. So we are doing this, designing this at the IP level. Now you could have IPs, RISC-V IP, you could have x86, you can have different architectures, different kind of IPs from different vendors, different processes, right? And they all need to be working together. How am I going to imagine what entities it's going to be interacting with? And what is the implication? And what is it that I need to design? What is the interface specification? What kind of assumptions I can make on the interface, right? And ensuring that the design trade-offs that I'm making with the functionality, the features that I want versus the safety functions. Do I want to implement all of the safety functions that I identified? Oh, maybe my assumptions were wrong. Maybe if I tweak my assumptions, it'll make my life easier to implement the safety functions. Then this next challenge is that doing the fault analysis to identify the random failures. Oftentimes, it is dependent on the functionality to be implemented first, because the fault analysis happens at the gate level. So you need some kind of functionality there, or from the gate level analysis, and that's when you know, oh, there are so many faults that cannot be detected within this particular failure time, or I don't have safety mechanisms, or I don't have mitigations that can actually that can actually fix or mitigate this issue if this fault makes it to the output and turns out to be a hazard, right? And then the detection and control need to happen well within the FTTI. I guess this is an obvious thing, right? Challenge number 3. Traditional fault models are unreliable. And I say this because we are used to using the stuck-it fault model. It's been the mainstay. But when you're talking about safety, you're not just detecting the fault. You also need to be able to detect the fault within a certain amount of time. Can it make to the safety mechanism? Can it make it to, can you detect and control it before it becomes a hazard? So what kind of a fault model do you need at the IP level? Right? Then the safety verification at the IP level, you can do all the safety verification. You can say, there are 99% of the faults that I can detect and I can control. But when you put it in a product, does it actually translate to something at the system level? How do you, because it depends a lot on what interacting entities are there, what are the other supporting functionality that exists in the rest of the IP. Right? And formal-based tools, they are inadequate for performing gate level analysis. They choke. I mean, even working at the RTL, we know the scope and the limits of using formal tools. But now we are talking about gate level analysis, making sure that a particular undetected fault cannot be detected or is masked, right? Proving. So let's say you have an untestable fault. What can you say about it? Is it something that you need to do? You want to resolve it? Do you want to write more tests and make sure that that fault is detected, or are you going to prove it? Right. So these undetected faults can pose a serious threat, and for all you know, it might not even be an issue. But resolving it and saying that this is not going to impact your safety or doesn't result in a hazard is something that's a tedious task. So let's switch to security. Security is the state of being protected against illegal access of assets, right? And asset is something of value, where you have data, encryption keys, or something like that, which you're trying to protect. Protect from getting stolen, from being overwritten, and also having appropriate access to it. Now, an attack is a deliberate action with a malicious intent performed to compromise that asset, right? And an example is the WannaCry ransomware attack, where an attacker basically locks up your data and demands some ransom in some crypto or something. So what you're seeing is a picture with a basic framework of security, where you have assets and there are threats. You're trying to protect this asset, but at the same time, you want legitimate users to have access to these assets, and you have some exposure. And these threats are constantly lurking around, and there are some security measures that you're trying to put in place to make sure that only legitimate users have access to these assets. So in the security domain, you have the CIA triad where you are classifying the attacks into three main categories, which is confidentiality, integrity, and availability. Confidentiality is basically a set of rules or the property of the asset where you are restricting the access of the asset for approved users only. Integrity is the maintenance and making sure that that particular asset is not overwritten or corrupted. You can rely on it's trustworthy. When you have a particular asset, you can rely on the consistency and the accuracy of that asset. Then you have availability, where you can just protect it and disconnect it from all other computers, but then it's going to be useless, right? You can put the asset in a secure place, but that's not the point of security. Security is not about just locking up and having no access to it. That's useless. So you want to be able to provide that you can assure that that asset is available to legitimate users when it is required. Now, any action that could compromise any of these properties is referred to as a threat. You might have heard of these two terms very commonly thrown around. One is vulnerabilities, the other is weakness. A vulnerability is a flaw or an error in the system that can be used to carry out a threat. So, for example, the bypass of normal privilege checks needed to access data belonging to the OS. This is a meltdown, right? And then a second example is Spectre, leakage of data through observable properties of speculative execution, and branch prediction. So there are these observable properties that can result in the security being compromised. A weakness takes it one level down and says it's a design flaw that could potentially contribute to the introduction of a vulnerability. So for the same two examples, you have the processor optimization that removes security mechanisms, which causes the vulnerability meltdown. Second, if you look at the second example, information exposure through microarchitectural state after a transient execution, right? So you might end up exposing the information through a microarchitectural state, which we thought was protected. If it's a microarchitectural state, it's not visible, should not be visible, but attackers can gain access, and they make an observable impact, which can be interpreted by an attacker, and the data could be leaked. So let's look at some chip level vulnerabilities. This is the test and debug infrastructure, where one chip acts as a debug host for the other. So we thought this is a new feature that we can use instead of testing it using a board or at speed, and this is something that we can use as a debug host when you have problems in silicon. But let's say you don't reconfigure it before you ship it out. This becomes a security vulnerability because the privilege escalation from by one chip basically compromises what you can get from the other chip, right? Because if you don't disable the debug configuration before shipping out. Similarly, the other one is a root of trust. This is a router where the FPGA is the root of trust, but you can overwrite it from a spy flash memory, right? So if it can be modified, if the root of trust itself can be modified, then you lose all the ability of protecting it, and then it can be taken over by an attacker. And then Spectre and meltdown that most of you have heard at least. These are basically microarchitectural efficiencies, speculative execution, out-of-order execution, branch prediction. We are trying to bring in all of those as a means to improve the performance, but Since these are microarchitectural states, these are microarchitectural features, these are not supposed to be exposed to the outside world. And similarly here in this case, DVFS, that's another capability that you have in the design. And but these are software readable, these are software observable. They exhibit properties, some observable properties that can be read by an attacker and can be interpreted to conduct attacks. But why hardware, you might ask? This is something that I pulled from MITRE. These have been increasing exponentially, right? If you see in the last 10 years. What's happening is hardware is being increasingly relied upon as a root of trust. And then when you have a root of trust, it makes it very valuable for an attacker to attack the root of trust because the ROI is pretty high. Because once it's baked in, it's hard for you to go and fix. There are very few mechanisms through which you can fix something that's broken in hardware. And it involves lots of investments in cybersecurity, lots of reaction time. The credibility of companies get affected. So the ROI is pretty high. The second thing is we have aggressive power and performance optimizations. What this means is you keep your design highly configurable, right? I'm sure all of you know about chicken bits. For power, when you introduce these new performance features, you want to make sure that if there is a problem for a certain feature, you might want to disable. You might, if there is a problem with some security, if there is a security vulnerability, you might want to change. So there are these chicken bits that you have for in your design. So when you are trying to introduce all of these new features for maintenance and doing aggressive performance optimizations, you are increasing the likelihood of vulnerabilities that are remaining undetected, because there are some set of known vulnerabilities, something that are disclosed, something that are studied. Yes, you are protecting against those. But what about these zero-day vulnerabilities that lurk around because you've optimized it for something, you have a microarchitectural optimization in your design? And then there is an increasing shift towards hardware-based security architectures. What it means is the previously existing security vulnerabilities that are there in software now make their way into hardware, because hardware, when you design it, it's the same process. You are going through it, you can't detect all the vulnerabilities. The vulnerabilities that were existing in software, they make it into hardware. So you have more vulnerabilities in hardware. So what's the first challenge? The IP level scope, as I group them into. And IP security is foundational. If you miss out something at the IP level, it makes it much more difficult when you integrate it into a product and have the security working for you. And the security requirements are many times out of context, because you don't know where it's going to be used. Is it going to be used in some military application, or is it going to be used in a toy, right? You don't know. And in which case, the IP, the kind of security requirements that you have are most of the time out of context. Then the specification cannot capture all the malicious intent, all possible malicious. It requires you to think like a malicious person yourself. The risk analysis, therefore, becomes highly subjective. Again, there's a common aspect with safety, because your risk analysis is now subjective. Should I mitigate this? Is this really a threat? How do you convince your architects that, hey, this is a threat, you need to mitigate this? And they'll say, no, I don't have the bandwidth or the budget to actually implement these security mechanisms. I need to improve these features because this is what is going to sell. So unknown ROI for the mitigations that you put in. So saw this picture in San Francisco while I was at DAC. I thought it was something that was very relevant. You can't fix every vulnerability. So don't. Fix those that are attackable. But what is attackable? And that's where we come into this concept of weaknesses. So I want to share with you, so I've given a definition or a differentiation between vulnerabilities and weaknesses. But what I put together is I pulled the top 10 hardware security weaknesses from MITRE, which is, I don't know how many of you are familiar with it. This is a nonprofit that collects all the vulnerabilities, categorizes them, extracts out the weaknesses. But if you I don't want to go through all of them, but the first one, improper isolation of shared resources on system on chip. This is the description of the weakness. But what's the impact at the IP level? You want to be able to disable resource sharing between untrusted agents, right? Then the other vulnerability to look at or weakness to look at, security sensitive hardware controls with missing lock bit protection. This is the description I just pulled off as it is. But at the IP level, you want to ensure that the appropriate lock bit protection mechanism is implemented and implemented correctly. Then you have improper restriction of software interfaces to hardware features. Ensure access control for software controllable features such as frequency and voltage. This goes back to the platypus vulnerability that I showed. Then you have sensitive information uncleared before debug or power state transition. And during state transition, you want to ensure that the data is cleared. That is, whatever is not required for the next state is cleared. So why is security verification so difficult in hardware? And for this community, this is more relevant, right? Attacking is fundamentally easier than protection. This is general truth, right? Offense is much easier. You can wait, choose your time and place, and it may perform this attack. And attackers need just one vulnerability. They're smart enough. They can use that vulnerability and they can conduct that attack. Whereas verification requires that you get all the 100% of all the vulnerabilities that exist. You are covered, and you know what these vulnerabilities are. Just being aware of what these vulnerabilities are is impossible, right? And proving the non-existence of unknown vulnerabilities is impossible. You don't know what these vulnerabilities are. They exist even before even the product ships out. And then attack-oriented bug hunting. This is a term that I came up with. That is, you're thinking with the mindset of an attacker, right? That means you need to think literally out of the box, not like a verification engineer trying to satisfy a spec. You're trying to break the spec in all possible ways. So sometimes you have to think about yourself with that malicious mindset. You have to wear that hat and actually being able to break and imagine how a particular weakness can be exploited. This is what makes it so difficult. So challenge number 2 are the verification tools and methodology. So today we have, if you broadly classify the kinds of requirements that you get, there are functional requirements and there are data protection requirements. Functional requirements are something that we are familiar with, or a lot of us are familiar with doing functional verification. FSM must never transition to secure state after reaching a test state, right? This is something that we understand. CPU must not be interrupted if running secure code. Very much in line with what we do for verification. But then there are these data protection requirements. Data in secure location must not be visible to the CPU if it is not in a secure mode. How do you ensure that any data is not, or even a part of the data is not going to a software visible register, right? Same with secure registers. The second one, secure register must never be overwritten by a non-secure agent. Must never be overwritten. That's a very broad definition, right? So the first set of requirements are within the scope of our SVA-based verification. I'm not saying that we don't have anything, any techniques. So we can write SVA specifications. This can be written, and it lends well with what we know on how to verify these requirements. The challenge is here, where you have the data protection requirements. How do you write these in SVA? You basically have to identify all the propagation paths through which this data can leak, right? And then that's getting that, and then did you identify just one path? Maybe there are more paths. How do you get this going? So the legacy EDA solutions that we have, by legacy I mean all the ones that we are familiar with, all the simulation methodologies, all the UVM, the formal verification, they are not adequate to meet the requirements to detect these. Then big question, how do you measure coverage? So this is a picture that depicts safety versus security. So we saw some challenges in safety, we saw some challenges in security. Then security, as I see it, is saying how do we prevent the environment from affecting the system, right? On the other hand, safety is about how do you prevent your system from affecting the environment, right? They both go hand in hand. And what happens when security meets safety? Or in other words, devil meets Murphy, right? So some examples here. Okay, so we have the safety applications that many of us are familiar with. Patient-controlled drug delivery, braking system, avionics, nuclear power. These are traditionally, we understand the safety aspect of it, but combine this with the security aspect. Now, if any of these are, these need to have the same level of security, increased level of security, these have security requirements in addition to safety, right? All of these applications. Any of the compromise, a compromise of security is detrimental to any of the safety aspects of what these applications require. So what are some of the challenges with coexistence of these requirements? Safety hazards can potentially cause a violation of the security goals and vice versa. I'll give you some examples. A security attack may result in a new safety failure mode, right? Previously, that was thought to be benign. An example would be a fault made observable through a malicious attack. A safety failure mode could cause a security vulnerability that was previously considered secure. Let's say you have a fault on the access control enable signal. This may expose the register contents to the external interface. And then we have the long product safety lifecycle, right? And the development lifecycle that makes threat modeling so much more difficult. What are the potential conflicts and requirements? Trade-offs between performance overhead to process the security functions versus safety. In other words, conflict between fail-safe state and fail-secure state. The countermeasures for a security threat could make the safety hazard even worse. The security threat of a malware trying to read out the private keys, right? So you have an HSM, you have some private keys. If these are read out and or if you have a way to forcefully overwrite its firmware, that's compromising the safety. And let's say it's detected and the countermeasure actually shuts down, this becomes a violation of the safety. Yes, you've ensured that it is secure, but it is not safe. So some examples here. Again, I won't go through all of them, but let's pick the authentication of check integrity of flash content. Authentication is okay, and this is a function that you want to implement. But the risk is the authentication is okay while the flash is not corrupted. Okay, so it's low impact for both of them. But let's say you have a side channel attack, and the asset signal is high when there is no attack. Means that the impact is high for safety and high for security. And this could become a denial of service depending on how frequently this happens. Or you have a decrypted data of decryption of a secure data. And the decrypted data is erroneous, right? In this case, safety, the impact is pretty low. But for security, it's pretty high. So these are some of the examples of safety and security failures existing in the same IP. So summing it all up, safety and security are key pillars of dependable computing. IP from multiple providers are used in products, which means that you need to be aware It makes it challenging on how to implement the safety and security features. That the assumptions of use could have a significant impact. This is where you would want to spend the most amount of time, do due diligence, and make sure that you get these assumptions right before you go about implementing and verifying. Then you need customized solutions. Not you can't take solutions as they are, because the challenges are a little different. They need specialized solutions. And then both requirements within the same IP can make these challenges a lot more challenging and increase the challenges multifold. Thank you. I hope I've been able to convey some of the challenges and motivate you to work in this area if you're not already working. But if you have any questions or comments, please email me.
Okay, thank you very much. Thank you. Unfortunately, Vivek can't take questions. It's quite a big day for ARM, and ARM legal said no questions in case. So unfortunately, we're going to go straight to our next speaker. But you're hanging around, aren't you, Vivek? Yeah. Thank you.